Applications of propositional logic. There are different ways to express the conditional statement. If P, then Q. This is the usual way. But we can say instead P implies Q, or P is sufficient for Q, Q if P, Q whenever P, Q is necessary for P, P only if Q, Q unless not P. This is equivalent to Q or not P. And in this problem, it is left for you to check that Q or not P, and if P then Q are equivalent by constructing the truth table of this conditional proposition. If P then Q, you have that truth table in the definition of implication. Translate the given statement into the language of propositional logic using the proposition provided. You cannot edit protected Wikipedia entry unless you are an administrator. Express your answer in terms of E. E means this proposition. You can edit a protected Wikipedia entry. And A, which is this proposition. You are an administrator. Not E unless A. This is what we are told here. Unless, before unless, we have this proposition which is denoted with E. Here it is negated, so it is not E. E negated is here before unless. After unless, we have you are an administrator, which is denoted with A. So our proposition can be written symbolically like this. And now, according to the last row here, this is equivalent with A or not E. But A or not E, according to the problem, this problem, is equivalent to E, if E then A. If E then A. The next problem is 2 on page 23. You can see the movie only if you are over 18 years old or you have the permission of a parent. Express your answer in terms of M, which means you can see the movie. E, you are over 18 years old. And P, you have the permission of a parent. You can see the movie only if you are 18 years old or you have a permission, the permission of a parent. So we have this here. This is M, only if E or P. M only if E or P. And this is in parentheses here. So this means P only if Q means it's another way of saying if P then Q. So M only if E or P is the same as if M then E or P. Problem 4. The use of wireless network in the airport. To use the wireless network at the airport, you must pay the daily fee unless you're a subscriber to the service. Express your answer in terms of W. You can use the wireless network at the airport. D. You can pay daily fee. And S. You are a subscriber to the service. The connectives here are must and this unless. So D or S is a necessary condition for W. D or S is a necessary condition for W, which means if W then D or S. Here parentheses are not required because this junction has priority to this implication. The next topic is system specifications. Translating sentences in natural language, such as English, into logical expressions is an essential part of specifying both hardware and software systems. System and software engineers take requirements in natural languages and produce precise and ambiguous specifications that can be used as the basis for system development. System specifications should be consistent, that is, they should not contain conflicting requirements that could be used to derive a contradiction. When specifications are not consistent, there would be no way to develop a system that satisfies all the specifications. Example, determine where these system specifications are consistent. The diagnostic message is stored in the buffer or it is retransmitted. So symbolically this is P or Q. P is the preposition before and Q is the preposition after. Or the diagnostic message is not stored in the buffer. This is not P. If the diagnostic message is stored in the buffer, then it is retransmitted. If P, then Q. So the specifications are written symbolically here, the same. All we have three specifications. All those are true when P is selected to be false and Q is selected to be true. Q is true, so pure Q is true. Q is true. P is false, so not P is true. And if false, then true is true. So all we found values for such that all specifications are true and the system is consistent. Problem 12. Are these specifications consistent? If the file system is not locked, then new message will be queued. New messages will be queued. Not locked. So if not locked, then in this case queued. If the file system is not locked, then the system is functioning normally and conversely. If not locked, if and only if the system is functioning normally. And conversely, that means if and only if system is functioning normally is denoted with F. If new messages are not queued, they will be sent to the message buffer. Not queued, then sent to the message buffer. If the file system is not locked, then new messages will be sent to the message buffer. If not locked, then sent to the message buffer. New messages will not be sent to the message buffer. This is just not B. So we have these specifications that we wrote symbolically already. Now make selections. We have L, Q, F, B. We try to make such selections that all these specifications are true. If L is selected to be true, then not L is false, and this Q doesn't matter. This will be true implication. L is true, this is false. We have equivalence here, so in order for the equivalence to be true, F must be also false, like not L. Q is selected to be true, because B is false. B is selected here to be false, so Q must be true, and L must be true. Not B will be true. So for this selection, all the specifications are true and the system is consistent. The next topic is logic puzzles. An island has two kinds of inhabitants: knights, who always tell the truth, and their opposites, knaves, who always lie. You encounter two people, A and B. What are A and B? If A says B is a knight, and B says the two of us are opposite types. Solution: we consider two cases. A is either a knight or a knave. So we have two cases that we should consider for A. In the first case, we consider that we assume that A is a knight. So this person must tell the truth always. Since the person A says B is a knight, this must be a truth. So B must be a knight. Both are knights, and the statement of B, the two of us are opposite types, will be a lie. But B, being a knight, cannot lie, so this is a contradiction. This means that case 1 is impossible. So it follows then that case 2 must be in place. That is, A must be a knave. Since knaves always lie, A says here B is a knight, so this must be a lie, which means that B must be a knave. So B has told the lie. The two of us are opposite types. Yeah, it is a lie. Both are knaves. So this is what we conclude. Both persons are knaves. Problem 25. You again meet two persons on that island. The person A says, I am a knave, or B is a knight. B says nothing. What are these persons? Again, consider two cases for A. In case 1, A is a knave. Now, the proposition I am a knave or B is a knight is true, because we have or, and one of the proposition is true. So the whole statement is true. But knave must lie. So we have a contradiction. So this case is impossible. Thus, case 2 must be in place. That is, A must be a knight. Now what the knight has said must be a truth. I am a knave is false in this case, so the other part of the disjunction must be true then, in order for the whole disjunction to be true. That is, B must be a knight. So the answer is A and B are knights. The next topic, logic circuits. Propositional logic can be applied to design of computer hardware. A logic circuit or digital circuit receives input signals P, Q, and so on R, each of them a bit, that is either 0 or 1, and produce output signal that consists of one or several bits. Here we'll consider only one output, one bit output for the circuit. Logical circuits corresponds to compound propositions with truth values f and t replaced with binary digits 0 and 1. We can use the logical operation we already know for logic circuits. Complicated logical circuits can be constructed from three basic circuits called gates. The inverter or NOT gate takes an input bit P and produces the output NOT P. The OR gate takes two input signals P and Q, each a bit, and produces the output signal P or Q. And finally, the AND gate takes two input signals P and Q, each a bit, and produces the output signal P and Q. We use combinations of these three basic gates to build more complicated circuits. And this is how inverter is drawn. This is OR gate and this is AND gate. In this problem, we have to construct a logic circuit using inverters, OR gates, and AND gates that produces this output from input bits P, Q, and R. So we have P, Q, and R. So I'll put R in the middle. They start traveling on these wires. Then here we need not R. So I'll draw inverter. Then we need AND of those two. So here I need an AND gate. So here I have not R. Here I have P and not R. Then I need to obtain not Q. So apply here negation or inverter gate. Here R travels along this wire, and then I need an AND gate. Another AND gate here. Here I have not Q. Here I have R. And this is not Q and R. Then I take those two and send them to an OR gate. And here I have P or P and not R, or not Q and R. Okay.